This is the screencast for section 2.3, example 5, the intermediate value theorem for continuous functions. Now throughout this course you're going to find a bunch of theorems that all sound alike, kind of do the same thing. This is one of them. I don't know what else to tell you about that. It's just going to be hard to remember what this is, so you got to work at it. I like to remember this as if it's an intermediate value. Intermediate means between. What the intermediate value theorem says is that on a continuous function, for any a comma f of a and b comma f of b, between a and b, there has to be every y value between f of a and f of b on that function. So in other words, it won't take on two y values without taking on every single value in between. I mean, it's like saying connect this dot and this dot without using this point. No. Okay, wait, how about no? I mean, you have to cross through every single y value in between f of a and f of b on a continuous function. Now we use this to show that a number exists, usually 0 because it's easily shown between positives and negatives, like you'll see here in example 5. Example 5 asks, is any real number exactly 1 less than its cube? So the answer is going to be yes or no, but you got to show a lot of work to support that. I'm going to say that there's a number x that equals itself cubed minus 1. So if I set this equal to 0, I get x cubed minus x minus 1. Now, I don't know, my best guess here would be to plug in something pretty large and something pretty small to find a positive and a negative output. But at the same time, large numbers are hard to work with and small numbers are sometimes hard to work with in terms of negative values. So I'm going to try f of 1 because I know that's pretty easy to plug in. And I get a negative, so that's good. How about f of 2? I get a positive. So since f of x is a continuous function, and we know that because, first of all polynomials are continuous functions, because we have a continuous function minus a continuous function minus another continuous function, or plus, depending on, from theorem 6 in the last example. So since f of x is a continuous function, and f of 1 here is less than 0, f of 2 is greater than 0, there must be an x value so that f of x equals 0 by the intermediate value theorem. Number 46 adds on a little bit of a challenge. Is any real number exactly 2 more than its cube? And we actually have to find that such value accurate to 3 decimal places. Not too much of a challenge, but not bad. So we're going to call this number n, and it's going to be n cubed plus 2, 2 more than its cube. So I'll set that equal to 0. Now I don't know exactly what number is going to solve this whole thing, but if I plug in 1, I get 2. If I plug in negative 5, I get negative 118. I mean, I just took a wild guess here, and I got a positive and a negative, so I know that there's going to be some x that I can input in here that will create an output of 0. So since f of n, which we have said is n cubed minus n plus 2, is a continuous function, and f of 1 is greater than 0, but f of negative 5 is less than 0, and I could have picked f of negative 2 or negative 6, it doesn't matter. There exists an n value somewhere in between 1 and negative 5, so that f of n equals 0 by the intermediate value theorem. And I found that n equals negative 1.521. Again, between positive 1 and negative 5, because 1 outputted positives, negative 5 outputted negatives. So between 1 and negative 5 is the perfect n value, negative 1.521, that made its cube plus 2 equal to itself. There it is.